The sharp ridges and deep troughs of a mountain valley are evidence of immense mechanical trauma. These landscapes were physically crushed and carved by the advance of continental ice sheets. Usually, liquid water naturally shapes the earth. A river follows the path of least resistance, flowing around obstacles and wearing them down grain by grain. Moving ice operates as a solid-state friction engine. It forces its own path, shearing straight through solid bedrock, regardless of the pre-existing topography. This expanse of ice provides a sense of the scale involved. During historical glacial periods, sheets thousands of feet thick smothered regions like the Irish Midlands, moving under their own staggering weight. To understand how ice manages to overwrite solid rock, we have to look past the surface and focus on the microscopic physics occurring at the very bottom of the glacier. We will track this engine across 3 distinct zones of impact: the aggressive erosion of the high uplands, the depositional patterns of the lowlands, and the deep deformation of the Earth's crust itself. These physical laws prove that glaciation is the ultimate sculptor of modern topography, capable of permanently overriding millions of years of river history in a geological instant. We begin at the microscopic scale, at the exact interface where thick, slow-moving ice grinds against continental bedrock. This diagram illustrates what happens when hundreds of meters of solid ice sit on top of jagged rock. That mass translates into intense localized pressure pressing downward onto the rock floor. That intense pressure forces the ice at the very bottom to melt into liquid water, even when the environment is below zero. This highly pressurized meltwater immediately infiltrates the existing cracks and natural joints in the bedrock beneath the glacier. When pressure drops or the temperature dips, that trapped water rapidly refreezes. This creates a physical bond, welding the main body of the glacier to the fractured rock. As gravity pulls the massive glacier forward, it physically rips those chunks of rock out of the earth. This is plucking, and it leaves behind a jagged, uneven rock surface. These plucked rocks now form the basal load. This payload transforms the glacier from a block of frozen water into a destructive mechanical tool. Pure ice lacks the friction required to deeply scour a landscape. To cut into solid rock, the glacier must use the debris it has already collected as a grinding agent. Here we see the process of abrasion. As the glacier slides forward, the rocks embedded in its base are continuously pressed into the bedrock floor by the weight of the ice above. This creates an industrial-scale grinding effect, similar to a sheet of coarse sandpaper stretching across the terrain for hundreds of meters. Abrasion leaves distinct evidence on the bedrock, parallel scratches known as striations, which indicate the exact direction of the ice movement. This constant pulverizing force grinds solid stone into a fine, powdery substance known as glacial rock flour, which gives glacial meltwater its characteristic milky appearance. Glacial erosion is a self-sustaining cycle. Plucking provides the abrasive tools, and abrasion uses those tools to scour the earth deeper. In the high uplands, this basal engine scales up to carve massive topographical features. A cirque, or corrie, begins as a shallow mountain hollow where snow accumulates and weathers the rock through nivation. As years of compacted snow turn into thick firn ice, gravity triggers a process called rotational slip. The ice begins to move in a rotational, grinding motion inside the hollow. This spinning motion uses the plucking and abrasion loop to hollow out the mountain, creating a deep, armchair-shaped depression. At the exit of the bowl, the ice is thinner and less erosive, leaving a raised rock lip. When the ice melts, this lip dams the water to form a tarn lake. When 3 or more of these cirques erode backward toward the same central point, they create a sharp, jagged pyramidal peak, like this one here. Eventually, the ice overflows these mountain bowls and enters the pre-existing river valleys below. This model highlights the mechanical difference between water and ice. Rivers cut downward to form V-shapes, but glaciers use their immense mass to erode both the bottom and the sides simultaneously. As the glacier moves in a straight line, it shears off the interlocking river spurs. This lateral force leaves behind the wide, flat floor and steep cliffs characteristic of a U-shaped valley. These upland features represent nature's brute force, completely overriding the delicate, winding paths established by water. As the ice sheet moves into the lowlands, the mechanical engine loses kinetic energy and begins to melt. When the ice can no longer support its load, it drops its entire payload of fragmented rock, creating a landscape of deposition. This material is called till, or boulder clay, a chaotic, unsorted mix of silt, sand, and boulders. The friction of the passing ice sheet molds this till into massive swarms of hills known as drumlins. A drumlin's shape is directional. The blunt stoss end faces the direction from which the ice came, while the tapering lee end points in the direction of the ice flow. Mapping these drumlin swarms allow geologists to reverse engineer the exact trajectory of the vanished ice sheet. In these same regions, we find a different geological structure, the esker. Unlike the chaotic till of a drumlin, an esker consists of perfectly sorted sand and gravel. This sorting indicates that the esker is the fossilized bed of a subglacial river. These rivers flowed through pressurized tunnels inside the ice sheet, depositing sediment along their path. When the ice melted, the sediment was left behind as a winding ridge. Lowland deposition provides a topographic record of thermodynamic failure and the routing of meltwater beneath the ice. We must now shift our perspective from the surface to the entire Earth's crust. A continental ice sheet's mass exerts enough pressure to bow the lithosphere downward. When the ice vanishes, it removes billions of tons of weight. This triggers isostatic rebound, a slow vertical springback rising towards its original elevation. This invisible crustal movement directly impacts the surface water systems we see today. As the land rises over millennia, the gradient of existing rivers is steepened. This rejuvenates the river, giving it a sudden boost in energy. This kinetic energy forces the river to cut deeply and vertically into its own established bed. This vertical erosion creates gorges and nick points, explaining why waterfalls appear in otherwise flat terrain. The cycle of glaciation scales from the microscopic melting at the base of the ice to the macro deformation of tectonic plates. The landscape is still reacting to these forces. Every modern river profile is still actively adjusting to the massive legacy of a glacier that vanished thousands of years ago.